In this video, we're going to derive the pore pressure diffusivity equation coupled with poroelasticity. This is the basic equation that you need in order to predict changes of pore pressure in 3 dimensions as a function of time, coupled with pressure gradients and also with solid deformation. All right, first of all, let's start with defining some variables. Here in this image, we can see a porous solid, which is filled with a fluid and can deform in the solid part and also in the pore space. If I wanted, for example, to compute how much fluid I have in the pore space, what I should do is multiply the volume of the pores times the density of the fluid. So for example, fluid mass is going to be directly the volume of the pores times the density, mass density of the fluid. All right, this is going to give us units of mass, but when we talk about a porous medium, in general, we want to refer to that to units of or mass per unit of volume. So in this case, if we just divide this by the bulk volume, what I get from here is that this is going to be just the porosity. And therefore, the amount of fluid in terms of mass per unit of volume is porosity times the density of the fluid. Okay, so let's use this definition in order to start deriving our equations. What we're going to study is the change of mass of fluid within the porous solid. And we have seen before that this equation represents the mass of fluid. By the laws of derivatives, I can derive this, or I can apply the derivative of the product is going to be the summation of these two terms, taking into account the derivative of the second times the first variable times the derivative of the second. For example, if I were to do this term to be exactly equal to 0, that's what is going to be defined as undrained loading, because there is no change of mass within the pore space of the fluid. Sometimes also this could be different than 0, right? And that means that there is some fluid that it is going to be displaced, or is going to be expelled or taken into the pore space that wasn't there before. So I wouldn't call that drained right away, because we don't know how much time it's going to take, and that's what we want to solve right now. Okay, so let's work with this equation, and for convenience, let me divide this by the density of the fluid. So the first term is just going to be the change of porosity, and the second term is going to be the change of fluid density divided the original density. All right, so from here, there are two things I can do. First, I hope that you remember that from the third equation of poroelasticity, we could calculate what are changes of porosity. And these changes of porosity, according to the theory of poroelasticity, are related to this equation, which depends on the Biot coefficient, the volumetric strain, the pressure, and the pore modulus. So if I were to take the derivative of this will be simply alpha is not going to change. The volumetric strain might change, so that's why I put the differential here. And the parameter n also is not going to change, but pressure could change. So I'm going to put the differential over there too. For the second part, we're going to take advantage of the definition of compressibility. The compressibility of a fluid, CF, is defined as the change of density of the fluid divided the original density of the fluid caused by a given change of pressure. And with this definition, and together with the definition of a bulk modulus, which is the bulk modulus is the inverse of the compressibility of the fluid, I can rewrite this term just by using, you see, here we have this part, so just by moving this change of pressure and talking about compressibility in terms of bulk modulus, the second part of the equation is going to be porosity is going to stay there, and now this is going to be change of pressure divided bulk modulus of the fluid. Okay, so I just need to do a few more steps in here, and let's continue by just regrouping these terms. Here I'm going to leave the change of volumetric strain, and notice that I have change of pressure in these two terms, so I'm going to use that as a common factor, and this is going to be the porosity divided Kf times the change of pressure. Notice here that alpha is a constant, n is a constant, Kf is, I'm assuming it is a constant, but porosity is not. Porosity is something that is going to change. So I'm going to do one more assumption over here, and I'm going to assume that the changes of porosity are much smaller than the original porosity. And this is going to be the assumption of small strains that we have used so far quite a bit, and it allows me to simplify many of my equations a lot. So instead of having just porosity here, I have initial porosity, and initial porosity, it is a constant. So all of this is going to be a constant or close to a constant if I assume the small strain equations, and this is going to be summarized in what is known as the Biot modulus, where the Biot modulus is defined as, and the Biot modulus is this m star, is defined as what I have over here, but I'm going to go one step further, and if you remember, we had an equation for n as a function of the Biot coefficient, the initial porosity, and the bulk modulus of the matrix, and here I'm just copying the rest of the equation. So we see now that this Biot modulus is a function of the poroelastic parameters, and is also a function of the compressibilities or stiffness of the solid, but also of the fluid. Now the fluid is playing a role, because the compressibility of a porous solid, if it is saturated and we do not let the fluid escape, is going to affect the overall bulk modulus. The fluid bulk modulus is going to affect the overall modulus. For example, if I have a porous solid filled with a gas which is very compressible, very likely when I compress it, if I do not let the gas escape, then the bulk modulus of the entire solid is not going to change much. But if I have that same porous solid filled, for example, with liquid mercury, then that's going to be a different story. The compressibility of the porous solid is going to be different. All right, so let me finish here by saying that this is the Biomodulus. Okay, let me see if I forget anything from here. And I don't think so. Just let me clarify here that we have defined before that 1 over n is equal to this equation. We found this in a few lectures before. Well, no, actually this was by proof, not by definition. 1 over n ks. Okay. Let's see what we do with this now. But basically what we've got so far is that the mass conservation within the porous solid now is also going to depend on the stiffness or compressibility of the solid part together with the compressibility of the fluid. All right, so let's bring now the continuity equation. Let me see if I can fit that in here. Okay, so this is going to be the second part of the derivation, and we're going to have to write the continuity equation for fluid flow in a porous medium. The continuity equation for fluid flow in a porous medium tells me that the change of fluid in the pore space as a function of time is going to depend on whatever gets in and out, and this is going to be obtained by the gradient of the mass of the rate of fluid flow in terms of mass. So this is going to be the density of the fluid times the flow rate Q. And this is a vector because it is in 3 dimensions. If I want to respect the continuity equation, which I should, continuity, or also here we're referring to mass conservation, this equality has to be equal to 0. So that's going to be a mass conservation. Whatever mass change I have in the porous solid as a function of time has to be due to a change in the flows, or whatever gets in is not the same as what it gets out. And if what it gets in is equal to what gets out, then this one should be equal to 0. That's basically the continuity equation. All right, so we're going to use the continuity equation together with what we just derived, which is, I lost my mouse, where is this? Okay, here, which is this. So you see, this term is going to be this one, and let's, just for the sake of completeness, let me rewrite this just to make obvious that what is the left-hand side term. Okay, so we're going to use this in here, and from this equation now I obtain that if I rewrite this, let me take the derivative of time outside, and what I have in here, I'm going to have to multiply times the density of the fluid, and what I have is all of this, and I'm going to use now my brand new definition of the Biomodulus. So this is going to be alpha, change of volumetric strain, plus 1 over the Biomodulus times a change of pressure. first term of the equation plus the gradient. And here I'm going to use Darcy's equation. Actually, I'm going to use isotropic Darcy, which means that the permeability is the same in all directions. So the Q's are just going to be given by, let me change this to a bracket. This is going to be negative K, where K in this case is permeability. Don't be confused with the bulk modulus. This is a little k. And this is going to be multiplied times the gradient of pore pressure. That is basically Darcy's equation. And all of this is going to be equal to 0. Okay, let's go ahead and let's take a look at this equation. And if you notice here, we have density of the fluid in this term, and also we have density in the fluid in this term. And the density of the fluid, because I'm assuming that this might change, it's a variable, so I cannot take it outside. But I could divide, though, by the density of the fluid outside this parenthesis, and after get it inside, that's valid. And I could get rid of those. And let's now then work on these derivatives one by one. The first term is just going to be this one. The second one is going to be the variation of pressure as a function of time. And this gradient, if I assume that permeability is the same everywhere, that will assume homogeneity of the porous solid. I can take this K and mu outside, also assuming that the viscosity is a constant, and this is going to be equal to K mu, the Laplacian of the pressure. And all of this equal to 0. Remember that going from here to here, we assume a homogeneous porous solid. That means that the properties, especially permeability, it doesn't change with time. Okay, let's do a little bit more of reordering in this equation in order to get our final equation. Usually these equations of diffusivity, we write them with the change of the variable that we're interested as a function of time on the left-hand side, and the variable as a function of space on the right-hand side. And let me keep the pressure here as function of time on the left-hand side. And when I do this, and I'm going to put this one on the other side, so this is going to be K times over mu, and I'm also going to multiply times the Biomodulus, so I just have this dp dt by itself on the left, and this is going to multiply the Laplacian of the pressure, and I'm going to move also this other term, alpha times Biomodulus times the variation of volumetric strain with time. And let me see, there is, oh, actually this should be negative. So this is a negative. And I obtained the equation that I was looking for. This is the diffusivity equation coupled with poroelasticity. I'm just going to write this shortly. You have the full title on the top. Poroelasticity. Okay, we have the equation. Let's now try to understand what it means. Maybe from previous courses that you have taken, especially on fluid flow, in hydrology or in reservoir simulation for petroleum engineering, you usually deal just with these two terms, the variation of pressure as a function of time, and here the variation of pressure as a function of space. And in here you have a variable that depends on permeability, viscosity, and compressibility of the fluid here on the denominator. And here we have something similar, but now this is the Biot modulus that incorporates all the physics that we have taken into account for poroelasticity. But it is very similar. The new term that I have now is this one. So now this term is telling me, for example, that I could have gradients of pressure which are equal to zero, and still I could have changes of pressure as a function of time which are not zero. And for example, here, if I had a compression as a function of time, which is making the pore space smaller, and I do not let the fluid go anywhere, then this equation is telling me directly what the change of pressure is going to be as a function of time, because the change of volumetric strain and not letting the fluid go anywhere. And basically this term, the second term on the right hand side, is the one that is going to do the coupling between fluid flow and deformation of the solid because of this term, the variation of the volumetric strain as a function of time. Okay, let's see. Let me add one more thing over there before we move to an example. Notice that the opposite is also true, in the sense that a change of pressure could also mean a change of volumetric strain. If I, for example, impose the change of pressure as a condition. And that's where the coupling is. Pressure affects volumetric strain affects pore pressure. Okay, let's try to see this in a few examples. If you wanted to solve this equation, then you could use the finite element method, finite differences, or any solution that you want, even an analytical equation. You can do this with reservoir simulators or with other simulators of pore elasticity that are going to allow you to solve this equation. We're not going to solve the equation right now, but let's talk about simple solutions and how to think a little bit more about these problems. The change of pressure as a function of time, as you can see, is proportional to this coefficient that we have in here. This coefficient, we can simplify it and call it a diffusivity parameter, where we could use this diffusivity parameter, and this equation, it happens in many problems of physics, and it has a general solution that, for example, if you have a step load or an impulse load, then from here you will get a characteristic relaxation time, which is going to be equal to L squared divided the diffusivity parameter, where, let me first put this, frame this equation. Okay, and what I'm doing here is that, for example, if I had a pore space, a porous solid, that I applied to it a rapid load, for example S, and this load changes as a function of time, through more or less in a step function. Let's do it now. Let's not do it a step. Let's do it a little bit different than the step, but it's quick enough that doesn't let the system relax. Then this characteristic time is going to tell me more or less what is the variation of pressure as a function of time. Let me use a little bit of color over here. That let's imagine that it is 0, and as soon as I load it, you would expect that this is going to increase quickly, and how much it takes for this pressure to decrease is going to be given by this characteristic time, where the characteristic time TCH is going to tell us more or less that the change of pressure is more or less 2/3 of the maximum change. If we apply an impulse load, then we're going to have an asymptotic behavior. So this is just an approximate formula, but tell us more or less how long we would need for that pore pressure to dissipate, where I'm missing one parameter over here. Let's imagine that we are loading this in the laboratory, and as we usually do, we load this with end caps on the top and the bottom, and if the fluid can escape, let's say that we have here our sleeve or our membrane that doesn't let the confining fluid interact with the pore fluid, then the only chance for the fluid to escape is through ports that I have in my end caps. So if I compress this very quickly, the only option of the fluid to escape would be by going either through the top port or through the bottom and escape through here. And the drainage length in this case is going to be this, and it is equal to that. If, for example, I had this port closed, then the drainage length will be the entire length of the sample, because the fluid, if it wanted to escape, if this one is closed, would have to go from here to there to this one, which is open. But if we have the two fluid ports open, then the length is just going to be, the drainage length is going to be half of the total length of the sample. And basically what this equation now is telling us is that this characteristic time is going to be proportional to the square of the drainage length. So the longer the sample, the more time you need for the pore pressure to dissipate, and it's going to be inversely proportional to the diffusivity parameter. The diffusivity parameter is what we had before, and we can approximate this diffusivity parameter just to the first component here. And you can see that if the diffusivity parameter is over here, the higher the viscosity, the higher is going to be the characteristic time, the lower the permeability of the medium, the higher is going to be the characteristic time, and also the bigger the modulus of the sample, the smaller is going to be the characteristic time. So all these variables are going to play a role on how much time it takes for a given sample and a given geometry to dissipate pore pressure. All right. So let me see if I forget anything. I don't think so. Uh, so if you, for example, wanted to analyze a test done in the laboratory and see if the test is either drained or undrained, or design the test just to obtain a drain or undrained response, what you should do is to compare the time of loading to the characteristic time of pore pressure diffusion. So here, if the characteristic time of loading is significantly higher, let's not use the time characteristic here. If the loading time is significantly higher than the, let's start with the smaller because it's what we see over here. It's going to be easier to understand. If the loading time is significantly smaller than the characteristic time of pore pressure diffusion, that would mean that this is close to undrained loading, because the time of loading is too fast or is too quick compared to the time the system needs for the pore pressure to be diffused. On the other hand, if the time of loading is significantly higher than the characteristic time of pore pressure diffusion given by this equation, then I'm going to have something closer to a drained loading, in which is quite unlikely that I'm going to generate extra pore pressure by loading the samples. Okay, let's see. We have a few more minutes before this video gets too long, and I have one example that I'd like to share with you here about the characteristic times for loading. And we're going to come back to this example in a little bit, but let me invoke this example here, because that's going to give you a good idea about what these characteristic times are. Okay, so here's the example. Let me bring this window into my other screen. Okay. In this example, we have the loading of a geological formation in which we have draining possible only from the top. This resembles the process of sedimentation and compaction, in which, for example, I might have a shale here at the bottom, so the only chance for fluids to escape would be through the top. Let's say I had a sand on the top. And for this particular example, the drainage length then would be from here to there. Okay, we have seen the equation for the characteristic time. So let's try to think about this question. What would be the characteristic time for pore pressure diffusion for a 100-meter thick sediment, just with top drainage and with the typical permeability of a fine sand and its compressibility, and a typical mud rock with a very low permeability and similar compressibility considering water? If you do the numbers, you're going to find out that for sand, the characteristic time of pore pressure diffusion is about 1 day for this 100-meter thick column, while for the mud rock, it's 3,000 years. So hopefully you see the difference in these two processes, and we're going to see that this type of loading, and especially when you have problems of sedimentation in which the rate of sedimentation is higher than the rate of pore pressure diffusion, are going to generate undrained loading in mud rock formations in nature. This is going to happen naturally. Okay, I'll come back to this example just in a bit. Let's talk about some examples of undrained loading. And now we have a few more tools to recognize undrained loading. Undrained loading is a loading that happens too fast so that pore pressure cannot diffuse in that time. And also, if we have a very strict definition of undrained loading is what it happens when the fluid cannot escape from the pore space at all when you do a loading. All right, so let's see some examples of undrained loading. Just hang on a little bit more with this video. We're done with the equations, so don't worry about that. We're just going to see now some cool figures and some nice videos. Okay, so undrained loading examples. Example number 1 is something which is called liquefaction. Liquefaction occurs in the subsurface whenever an earthquake hits a soil and the waves produce a movement of the grains so that the grains reaccommodate and go from a loose packing into something denser, so that the pore space that was available before and was filled with water, now all of this is filled with fluid. In this case, let's assume water. So that when these grains accommodate and find the lower porosity, this water has to escape from there. And if it can escape, what is going to happen is that the pore pressure is going to increase. And if the pore pressure increases, that means that the effective stress is going to go down. And let's try to follow this story. So if pore pressure increases, this is going to mean that effective stresses are going to go down. And if effective stresses go down, that means also that the shear strength of this sediment is going to go down. Basically, this is what happens, or what you find when you have a quicksand. When you have a quicksand, the effective stress is so low that the shear strength is also very low, and everything sinks in a quicksand. And you can find this in nature in places in which there are some sediments which are loosely compacted, so that when an earthquake hits the soil or the sediment, it reaccommodates the grains, makes a pore pressure increase, effective stress go down, and some of these buildings to sink. And this is a huge problem. And this is because the undrained loading caused by the mechanical action of the waves. Let me show, let me actually share an example with you about this liquefaction problem. That this video is not 1,000 words, it's 1,000,000 words. let's see what's going on. Okay, here you have an example of liquefaction in Japan. And let me play the video. All right, so you see the level of the water going up and down, and you can also see actually the ground moving and displacing. So the action of the ground and porosity changing is what is making the fluid move. If you also take this at a grain scale, you may also remember what I was telling you before about squared flow that produces attenuation of waves in porous media. And it is very similar to this. I was looking for some other videos in which you actually see that the pore pressure increases so much that you have water geysers coming out uh, from holes into the ground caused by the liquefaction, or also some cracks that are produced with these processes. Okay, so this is partially drained and undrained loading because the fluid is moving. Example number 2. Example number 2 is about what is called disequilibrium compaction. Disequilibrium compaction is a phenomenon by which your rate of sedimentation is higher than the rate of pore pressure diffusion. Let me make this schematic and just complete it so it will make more sense to you. Okay, imagine a river somewhere over here that comes loaded with sediments, and these sediments eventually get deposited into a sedimentary basin. Sometimes you could have these sediments to be muddy, that means with clays, or sometimes also mostly with sands and silts. It's going to depend on what kind of sediments are being transported by this river and dumped into this sedimentary basin. Okay, here we're going to have two competing actions. One is going to be the rate of sedimentation. And let's use this m as a function of time, where m is the amount of sediments being deposited. If the rate of sedimentation is much higher than the rate of pore pressure diffusion, which is what we have seen before, what is going to happen is that some of these layers are going to develop what is called overpressure. And this is linked to the example that I was showing you before, in which, for example, for a mud rock 100 meters thick, you need 3,000 years to dissipate that pore pressure. So here I'm dumping sediment so quickly that the fluids inside some of these sediments do not have the time to escape from the pore space. And because they do not have that time to escape, what it happens is that when I go to the field and measure pressure as a function of depth, I'm going to find out the following. This is going to be depth. In the water region, my gradient of pore pressure is going to be hydrostatic. Once I get into the sediment, I don't know, but let's continue the hydrostatic trend. We have seen the vertical stress here is going to change slope, and it's going to start increasing faster than the trend of pore pressure. And if I do have this phenomenon of disequilibrium compaction in which the fluid cannot escape from the pore space, the pore pressure is not going to be hydrostatic. It's going to be higher than hydrostatic. Probably close to the seafloor, it might follow a trend which is similar to hydrostatic, but soon it's going to deviate from the hydrostatic trend. And that deviation is going to be caused by this phenomenon called disequilibrium compaction. We're going to see later on that we can take advantage of this phenomenon through the measurement of porosity in order to predict what this overpressure is. So this will be the hydrostatic trend. This one is the actual pore pressure. And this is another example of an unloading process in which over geological time we do not let enough time the process to achieve equilibrium, and we keep on loading it, or nature keeps on loading it, so that pore pressure remains high for over several years. Okay, this is example number 2, and we'll see this later on as well. Let's go with example number 3. Example number 3 is what we have, for example, around a hydraulic fracture. Hydraulic fractures are usually pretty quick, so that if you have material adjacent to the fracture, the fracture is not going to, the rock may not have enough time to relax and dissipate the pore pressure. Okay, so let me go by drawing this fracture. Let's imagine that we have a wellbore from which we're growing a hydraulic fracture. Goes into both sides, but we're just interested on this side. This is done, of course, in a porous solid. Well, let me delete this. I actually don't like this shading. So this is, remember, a pore space, a porous solid. Okay. We're going to see also later on, when we get to the physics of hydraulic fracturing, that what you apply on the face of the fracture is going to be a compression. This compression, if you do not let the pore pressure enough time to dissipate, may produce undrained loading. So the compression then is going to cause a change of the volumetric strain, which is equal to 0. And if there is not enough time for the shale to release the pore pressure, and that might happen very likely, for example, in an old shale, what we're going to have is undrained loading with an increase of pore pressure on the face of the fracture. This undrained loading could produce, for example, also increase of pore pressure and decreases of effective stress on the face of the fracture. So let me complete something over here. I'm assuming that I have a very low permeability. Let's say 1 microdarcy. This is what would happen on the face of the fracture. What do you think is going to happen, for example, at the tip of the fracture? At the tip of the fracture, in order for this fracture to propagate, I need to have tension. And this tension is going to cause an extension in the solid that if I had a change of the volumetric strain, which is higher than the 0, and that means that this one is increasing in size, then what this is going to produce is a decrease in the pore pressure, also assuming conditions of undrained loading. This is a very interesting phenomenon, because what this is telling us is that at the tip of the fracture we could decrease the pore pressure because of the extension or increase of volume of this element. So you should think, when we compress a solid and we don't let the fluid escape, then we have an increase of pore pressure in the porous solid. The opposite, when we increase the volume, then we're going to be applying a kind of a suction to the fluid, and therefore the pore pressure is going to decrease. Let me complete this over here, that I'm assuming, let me do it over here. The pore pressure is going to increase. And in this case, it's going to be the opposite. The pore pressure is going to decrease. And this is also something that is worth to mention, because I have seen some works in hydraulic fracturing that start with the pore pressure of the medium of the porous solid to be equal to 0. So eventually at the tip of the hydraulic fracture, what they compute is a negative pressure. Something that really cannot happen, but the pressure could be so low that, or you could decrease the pore pressure. Sometimes even some people say that you could cause cavitation at the tip of the fracture by this undrained loading in extension. But most likely you're just going to lower the pressure at this region. Okay, so these are 3 examples of undrained loading, and I hope that these were useful in order to illustrate what we have presented today rigorously through the equation of the diffusivity equation of pore pressure coupled with poroelasticity.